On June 8th, 2026, Apple made an announcement that seemed to crack open one of the most guarded systems in modern computing. Private cloud compute, the secure cloud behind Apple Intelligence, would expand beyond Apple's own data centers for the first time. Some demanding requests would run on Google Cloud hardware using NVIDIA GPUs, Intel processors, and Google's Titan security chip. It sounded like Apple was loosening its grip, admitting that even its private intelligence system could no longer live entirely inside Apple silicon. But buried inside the technical explanation was the sentence that mattered more than the new partnership or the unfamiliar hardware. Apple devices would trust only private cloud compute software that had been cryptographically approved and controlled by Apple. The walls of the data center could move. The machines could belong to someone else. The authority over the system would remain in Cupertino. That contradiction reveals the real architecture now forming around hundreds of millions of people and their most intimate digital records. Apple is not simply building another chatbot. It is building an intelligence layer that can read personal context across the operating system. Messages, photographs, reminders, calendars, documents, locations, app actions, and on-screen content can become signals inside that layer. Apple's promise is that much of this understanding happens locally without sending a complete personal profile to a conventional cloud service. That is a genuine privacy advantage. It is also the foundation of a competitive barrier that may be far harder to leave than iMessage ever was. Because the valuable asset is no longer only the photograph, contact, note, or file that a user can copy to another platform. The valuable asset is the invisible structure built around those records: relationships, meanings, permissions, habits, and predicted intentions. Apple calls this personal intelligence. Regulators call the company a gatekeeper. Competitors see an operating system they cannot fully enter. The question is not whether Apple secretly owns every piece of your data. Its architecture is designed to avoid exactly that kind of collection. The deeper question is who controls the machinery that turns private data into useful intelligence, and whether that intelligence can ever follow you. To understand the emerging wall, we have to begin with the feature Apple presents as its strongest defense: processing on the device itself. Now, for years, the dominant model of consumer artificial intelligence was simple. Your request traveled to a remote server, where a model processed it. You logged technical information there and returned an answer. The intelligence lived in the cloud. Your device was mostly a window. Apple reversed that emphasis. Its system was designed around models that could run directly on the iPhone, iPad, or Mac, drawing on information already present there. The pitch was not merely faster response or offline convenience. It was that the device could know more about you precisely because the company running the model did not need to collect everything about you. That distinction matters. A calendar event, a private message, a medical appointment, or an unpublished photograph can remain behind the device's security boundary while still influencing an answer. Instead of building one centralized profile in a distant data center, Apple can let the operating system assemble context at the moment it is needed. The hardware underneath this promise was not added for Apple Intelligence. It had been under construction for more than a decade. The Secure Enclave, introduced across Apple's product lines over successive generations, is a separate security subsystem isolated from the main processor. It protects cryptographic keys, biometric templates, and access to encrypted user data, even if the primary operating system is compromised. Every compatible device also sits on Apple-designed silicon, where processors, memory protections, media engines, and neural accelerators are coordinated with software Apple controls. On newer chips, protected memory can be shared with a secure mode of the neural engine, allowing sensitive machine learning tasks to use hardware acceleration without exposing raw biometric material to ordinary applications. This is the silicon-level fortress described in Apple's security documents. A unique hardware key is fused into each device. File system encryption is rooted in secrets that cannot simply be extracted by software. Secure boot verifies approved code. Memory protections attempt to stop one compromised component from reading another component's secrets. None of that is marketing fiction. These mechanisms create real obstacles for thieves, spyware operators, hostile insiders, and governments attempting to pull usable information from a locked device. They also establish an unusually tight relationship between the person's data, Apple's hardware, Apple's operating system, and Apple's rules for approved execution. The difference between protection and enclosure begins at that boundary. Strong encryption answers the question, who can read this? Platform control answers a different question, who can build the system that is allowed to use it? Apple's design increasingly joins those two questions together. Apple Intelligence depends on more than a language model. A general model can summarize text, generate an image, or answer a question. A personal intelligence system must discover which text matters, which person a name refers to, which app can perform an action, which record the user is pointing toward, and what permissions apply. Apple's App Intents framework is one of the quietest pieces of that machinery. Developers describe the actions and entities inside their apps using structures defined by the operating system. A task manager can expose projects and deadlines. A communications app can expose conversations and contacts. A photo editor can expose images and editing actions. Those entities can be contributed to the Spotlight semantic index, the system-level layer that makes content searchable by meaning rather than only by exact words. The same structured information can allow Siri and Apple Intelligence to discover content, connect a spoken request to an app, and perform an action without the user memorizing a rigid command. This is where personal data becomes something more valuable than a collection of files. The system can understand that the document Sarah sent after the meeting refers to a particular attachment, sender, conversation, and time. We can connect a message to a calendar event, a photograph to a location, or a reminder to something visible on the screen. The result is not necessarily one permanent dossier stored in a single database. It is a network of indexes, permissions, app declarations, local models, account relationships, and device state. Much of it can be generated on demand. Much of it may remain encrypted. Yet together it becomes the operating memory of the personal AI. That operating memory is where Apple's strategic advantage begins to compound. A competing chatbot can be downloaded as an app. You can ask for access to photos, contacts, a microphone, or selected files. But an app does not automatically receive the same system-wide visibility, action privileges, trusted execution path, or integration that the operating system reserves for its own intelligence layer. Even when Apple allows third-party models into its framework, the model and the personal context are not the same thing. In 2026, Apple announced a broader model abstraction layer, packages for models from Anthropic and Google, and open source implementations capable of running other local models through Core AI or MLX. That weakens the idea that Apple intends to ban every outside model. But it does not hand an outside provider control of the semantic index, the permission broker, the device trust chain, or the system experiences through which personal context becomes useful. A developer may swap the engine that generates an answer while still driving on a road designed, signed, and policed by Apple. This is why the emerging wall is easy to miss. It is not a simple ban. It is an architecture of unequal depth. Third parties can enter through approved interfaces, but Apple defines the interfaces, decides which private signals they expose, and controls the layers that connect intelligence to the rest of the device. There are sound security reasons for some of this. Giving every application unrestricted access to messages, health records, photographs, passwords, and background sensors would be catastrophic. A personal AI that can act across apps also becomes a powerful target. One poisoned instruction, malicious document, or compromised plugin could turn convenience into data theft. Apple's answer is to keep authority close to the operating system. Apps declare capabilities. Users grant permissions. Sensitive data remains compartmentalized. Models receive only the context needed for a particular request. More complex tasks can be sent to a controlled cloud environment rather than to an ordinary server where administrators may have broad access. Private cloud compute is the most ambitious part of that answer. When a request is too demanding for the device, the system can send relevant information to a remote model. Apple says the request is processed without being stored and without becoming accessible to Apple staff. The server is designed to operate without privileged runtime access. Before data is sent, the device verifies the software configuration of the remote system through attestation. It is meant to communicate only with approved releases whose measurements are recorded in a transparency system. Apple publishes software images and tools so outside researchers can inspect important parts of the environment and test whether the claims hold. The architecture also tries to prevent targeting. A malicious operator should not be able to route one chosen user to a specially modified server. Computation is intended to be stateless. Logs and debugging paths are restricted because the absence of an obvious administrative backdoor is part of the security promise, not an optional policy. These are substantial protections, and they separate private cloud compute from the familiar cloud arrangement in which a provider asks users to trust internal rules they cannot verify. Apple has also attached large security bounty rewards to failures that could expose request data or execute unauthorized code inside the system. Yet the same design makes Apple the final authority over the intelligence path. Even after the 2026 expansion to Google Cloud Infrastructure, Apple retained complete control over the private cloud compute software. The user's device would accept only configurations Apple had cryptographically approved. That is the crucial shift. Apple no longer needs to own every building, server rack, processor, or model component to preserve the wall. Control can be enforced through keys, signatures, entitlements, operating system APIs, and the decision about which software the device is willing to trust. In other words, the wall is not primarily about refusing all partnerships. It is about ensuring that every partnership terminates inside an Apple-governed system. Other companies can provide models, chips, or infrastructure. Apple remains the institution that decides how personal context enters, what code can touch it, and how the result returns to the device. This arrangement creates a new business model for personal data. Advertising platforms often profit by collecting information, linking it across services, and using it to predict what a person will click or buy. Apple's model can profit differently, keep more information private, then sell the hardware and services uniquely positioned to use that private information. Privacy, therefore, becomes both a protection and a product differentiator. The message is not, give us your data so our cloud can know you. It is, buy our devices because only this integrated system can know you without exposing you. The less comfortable users become with cloud surveillance, the more powerful that proposition becomes. This does not mean Apple's privacy claims are fake. A moat can be built from a real advantage. In fact, the moat is stronger when the advantage is real. If on-device processing and verifiable confidential computing genuinely reduce risk, leaving the ecosystem can feel like abandoning safety rather than merely changing brands. That psychological and technical combination is more durable than a proprietary charging cable. A cable can be replaced by regulation. A messaging standard can be adopted. A photograph library can be exported. But a personal intelligence layer becomes useful through accumulated context, trusted relationships, app integrations, and repeated permission decisions. Apple already lets users request copies of many categories of account data. It provides tools to transfer certain collections, including iCloud photos and Apple Music playlists, to other services. Contacts, calendars, documents, and photographs can often be moved through standard formats or third-party tools. Those capabilities matter because the claim that Apple literally prevents all migration would be false. The issue is what is not represented in an ordinary export. A folder of photographs does not include every relationship inferred among faces, places, events, messages, and future requests. A calendar file does not contain the complete action graph through which an assistant has learned to navigate a person's apps. Apple's public portability tools focus primarily on the records people recognize as their data. The emerging AI layer includes derived structures, semantic indexes, embeddings, local caches, app entities, authorization state, conversation continuity, tool preferences, and device-specific trust relationships. There is no widely adopted cross-platform package for exporting that entire operational context. Some of those structures should not be portable in raw form. Encryption keys tied to a device must remain secret. Biometric templates should not become downloadable files. Security tokens and protected credentials cannot safely be copied into a generic archive. A responsible migration system would need to distinguish personal meaning from dangerous secrets. But the absence of a safe standard still creates a switching cost. A user may be able to carry the original data away while leaving behind the system that understood how the pieces fit together. The new platform receives the photographs, messages, and appointments, then must rebuild the context from the beginning if it is permitted to rebuild it at all. This is the difference between data portability and intelligence portability. Data portability asks whether you can take your belongings out of the house. Intelligence portability asks whether you can take the house's memory of where everything belongs, how you use it, which doors you trust, and what you usually do next. As AI becomes more agentic, that distinction grows more important. A summarizer produces a temporary answer. An agent chooses tools, searches local records, performs actions, carries context across steps, and adapts to the user's routines. The value shifts from the model's raw intelligence to the quality and continuity of its access. Apple's 2026 developer tools pointed directly toward that future. The company described models that could reason over larger contexts, switch among tools and profiles, search local spotlight data, analyze images, and use private cloud compute for demanding tasks. It also extended access toward the watch, where personal signals are even more immediate. Each new capability deepens the benefit of integration. An iPhone knows communications and location. A Mac holds working documents and browser sessions. A watch records activity and delivers notifications. AirPods become an interface. A tightly coordinated system can answer with context no isolated app can easily reproduce. This is the strategic brilliance of the system. Apple does not have to persuade users to surrender privacy in exchange for intelligence. It can persuade them that privacy requires the intelligence to remain inside Apple's architecture. The safer the enclosure appears, the more costly the outside world can feel. Regulators have already encountered an earlier version of this argument. The European Union designated iOS, the App Store, Safari, and later iPadOS as gatekeeper services under the Digital Markets Act. The law requires access to certain operating system hardware and software features so third-party products can compete more effectively. In March 2025, the European Commission specified measures Apple had to implement for connected device interoperability. By mid-2026, the changes included or anticipated broader access to notifications, proximity pairing, Wi-Fi information, NFC functions, peer-to-peer connections, background execution, and parts of automatic audio switching. Those requirements matter to the AI story because they expose a long-running pattern. Features that make Apple devices feel uniquely seamless often depend on privileged operating system access. Apple may describe restrictions as necessary for privacy, security, battery life, or reliability. Regulators may conclude that at least some access can be opened safely. Neither side is automatically wrong. Interoperability can create attack surfaces, confuse permission models, and give poorly secured products access to sensitive signals. But security is not a binary property, possessed only by the platform owner. Interfaces can be documented, permissioned, audited, rate limited, and made revocable. The conflict is therefore about governance. Who decides what level of risk is acceptable? Who gets to test an alternative? Who can appeal when access is denied? And can the company that sells the competing device or service also be the sole judge of whether a rival's integration is safe? If Apple opens too little, competitors may be reduced to shallow chat windows while Apple Intelligence acts across the system. If it opens too much, a malicious or careless agent could combine fragments of information that no single app was previously able to see. The solution requires fine-grained controls, not slogans. Apple's architecture already demonstrates that fine-grained controls are possible. App intents expose selected actions rather than entire private databases. Semantic entities can retain attribution to the app that supplied them. Permission prompts, entitlements, sandboxing, and secure execution can limit what a model or tool receives. The unresolved issue is whether those controls will become neutral infrastructure or remain a strategic advantage for Apple's own intelligence. A neutral layer would let users choose among trusted assistants, grant them comparable capabilities, and revoke access without losing the underlying personal context. A proprietary layer can look open while preserving asymmetry. Third-party models may generate text through Apple's framework, but only Apple's assistant may receive the richest orchestration. Developers may expose app actions, but Apple can define the schemas and decide which system surfaces activate them. Rivals can participate, yet may still struggle to become the default intelligence. The 2026 model framework shows movement in both directions. Apple opened interfaces to outside models, announced open source components, and enabled local alternatives on its hardware. These are meaningful concessions to developer choice. They also make Apple's platform more attractive, increasing AI experiences that depend on Apple's APIs. That is why focusing only on which foundation model Apple uses misses the larger strategy. Models can be licensed, replaced, distilled, or routed to different providers. The defensible asset is the system that knows which data is relevant, can retrieve it safely, and has authority to act on the user's behalf. Apple's hardware requirements reinforce this advantage. Apple Intelligence originally arrived only on recent high-end iPhones and devices with sufficiently capable Apple silicon. The models downloaded onto supported hardware, and older devices could not simply gain the complete system through an app update. Some limits are technical. Local generative models require memory bandwidth, storage, neural processing, and power efficiency. Running them on weak hardware can produce slow, unreliable, or battery-draining experiences, but hardware-gated intelligence also turns privacy-preserving AI into an upgrade incentive. A cloud-only competitor can serve an old phone because most computation happens elsewhere. Apple's local-first approach makes the device itself part of the service. The privacy advantage and the hardware sales cycle become aligned. Better personal intelligence requires newer silicon, and newer silicon is sold by the same company defining the intelligence. The effect becomes stronger across multiple products. Once a user has an iPhone, adding a Mac, watch, AirPods, or iPad increases the amount of context and continuity available inside the same account and trust system. Each device is useful alone, but the network becomes disproportionately valuable as more pieces are added. Leaving then becomes a subtraction problem. The user is not comparing one phone with another phone. The user is comparing a functioning web of messages, authentication, photos, accessories, automations, purchased apps, family relationships, and emerging AI context against the work required to recreate it elsewhere. Personal intelligence could turn that work into a perceived loss of memory. The new device may contain the same files but fail to recognize references, routines, or relationships in the same way. It may ask for permissions already granted for years. It may not reach the same accessories or app actions with equal depth. The risk is not that Apple will encrypt your photographs and refuse to release them. The subtler risk is that the most useful interpretation of those photographs becomes inseparable from the platform. Ownership of the original record remains with the user, while practical control over the derived intelligence remains fragmented and non-portable. This is why privacy as a moat is more accurate than privacy as a lie. Apple can truthfully minimize collection, protect cloud requests, and limit employee access, while also gaining competitive power from the architecture. Ethical benefit and commercial strategy can occupy the same design. It is also why accusations of secret mass surveillance miss the strongest case. There is no need to claim that the neural engine is covertly uploading every action. The documented system is already consequential. Local models, semantic indexing, app integration, hardware-bound security, attested cloud processing, and Apple-controlled trust decisions. The debate should focus on verifiable boundaries. What information is indexed? Which apps can contribute entities? Which assistants can search them? Can a user inspect or reset the derived context? Can that context be transferred in a privacy-preserving form? Can independent agents receive equivalent capabilities under the same rules? Transparency is especially important because local processing is difficult to observe from outside. When data never leaves the device, conventional network analysis reveals little. Users gain privacy from remote surveillance, but may have less visibility into how the operating system interprets their information internally. A meaningful right to digital autonomy would require more than an export button. It would include the ability to understand what personal context exists, choose which intelligence provider may use it, transfer safe portions of that context, and delete derived structures without destroying the original data. It would also require portability standards that do not expose the very secrets privacy engineering is meant to protect. That is difficult, but not impossible. Systems could export user-approved semantic relationships in documented formats, reauthorize app actions on the destination, and rebuild embeddings locally rather than copying sensitive vectors blindly. Competition could push the industry towards such standards, but only if rival assistants can reach enough of the operating system to become credible alternatives. Otherwise, every platform will build a private memory palace, and users will be forced to choose not merely a device, but the only intelligence capable of understanding the life stored inside it. That future would reverse the original promise of personal computing. The personal computer was valuable because the user could own general-purpose hardware, install different software, move files, and decide how the machine should work. Personal AI could either extend that autonomy or replace it with a deeply personalized dependency. Apple is positioned to define the answer because its architecture joins hardware, software services, distribution, and privacy more tightly than almost any competitor. It can build protections that cloud-first companies struggle to match. It can also use those protections to justify boundaries competitors cannot cross. The company's 2026 expansion of private cloud compute showed both forces at once. Apple accepted Google infrastructure, NVIDIA accelerators, Intel confidential computing, and technology derived from Gemini. It opened the physical fortress because scale and capability demanded cooperation, yet it did not surrender the root of trust. Apple-controlled software remained the condition for access. Cryptographic approval, not ownership of the building, determined where personal requests could safely go. The wall had become more abstract, more portable, and potentially more durable. That same pattern may define the personal context layer. Apple can allow many apps, models, and infrastructure partners to participate while preserving control over the protocols that assemble identity, meaning, permission, and action. The ecosystem can appear increasingly open even as dependence on its central architecture deepens. For users, the immediate experience may be excellent. Requests can be faster, more relevant, and more private. Sensitive information can stay on the device. Complex tasks can reach powerful models without entering a permanent cloud profile. These are real improvements over much of the AI industry. The cost may surface only at the moment of exit. A person can move the visible data and discover that the invisible intelligence, the associations, workflows, trusted tools, and accumulated context that made the system feel personal does not have a destination. That is the choice Apple's strategy could quietly create. Not privacy versus surveillance, but privacy inside one integrated intelligence system versus autonomy across competing systems. The first problem is urgent. The second arrives slowly, hidden inside convenience. On June 8, 2026, Apple appeared to open its private AI cloud to the outside world. In reality, it demonstrated how little physical ownership matters once trust is enforced in silicon, software signatures, and operating system policy. The proprietary wall is not a single server, chip, app, or account. It is the controlled path between your private life and the intelligence permitted to understand it. The most durable lock-in may be the intelligence that knows you, but cannot follow you across the platform you choose.